to solve a system of 3 equations in 3 variables. All right, so the first thing I need to do is write out the equation, right? So it says, first thing, it is important to note that it does not matter which variable you choose to eliminate first or second, or the best choice of which variable to eliminate first. It will depend on the system. For the purpose of simplicity, the steps below will walk us through a solution in which we have decided to first eliminate z and then eliminate y. Step 1. Copy down the original system and visualize the final answer. Double check that it was copied down correctly or accurately. Next, think about the end goal. What is the final result we are after? For this problem, we will be finished when we have an ordered triplet of the form x, y, z. So the system is 4x minus y plus 3z is equal to -2. It's equation 1. Then I have 3x plus 5y minus z equals 15. -2x plus y plus 4z equals 14. So I am looking for a value for x, for y, and for z that will make every single one of these equations true. And I've put here, fill in the coordinates as they are found. So each time I figure out one of the values, I'm going to come up here and start filling in the blanks. Step 2, eliminate one of the 3 variables. Let's say z. So we'll eliminate z by adding transformations of the original equations 2 at a time to arrive at equations 4 and 5. So we're going to come up with 2 new equations, and these 2 new equations will only have 2 variables rather than 3. So we're using the system of elimination, or the method of elimination, to do just that, eliminate a variable. So I'm going to be eliminating z to come up with 2 new equations. So I'm going to use equation 1 to create equation 4. I'm going to use equation 1 and equation 2. All right, so equation 1, 4x minus y plus 3z. I'm going to use that with equation 2, 3x plus 5y minus z equals 15. That's my equation 2. I actually need to complete this. This was equals -2, and that's my equation 1. So then I want to cancel out z, so I'm going to be adding these together, and so I need to multiply possibly both equations, or maybe just one of the equations, by something so that the z's will cancel when I add them. And so it's convenient that the 3z up here and the -1z can be fixed with just one transformation. So I'm going to just do 3 on the bottom equation, and the top one I can keep the same. So I'm going to end up with a new equation, equation 4, after this is completed. But what I'm going to do first is the transformation, and then I'll add them. So I want to simplify this step first. So like I said, I'm going to keep the first equation the same. And multiply everything by 3 for the second equation. So I'll have 9x plus 15y minus 3z equals 45. So that's my second equation, just now in a new format. So that's an equivalent equation, 9x plus 15y minus 3z equals 45. Equivalent. If I were to be able to graph this, although it's 3-dimensional, so I'm not going to, but this would look exactly the same on the graph as this would. So now I'm going to add those together, and I'll get 13x plus 14y and 0z equals 43. And this is equation 4. So now I have only 2 variables in my fourth equation. I'm going to do a similar process now for finding the fifth equation, and I'm going to use equation 1 again for no particular reason other than for a simple approach. You could choose any 2 equations. You could eliminate any variable, but I'm eliminating z again because whatever you do on the first step to get the fourth equation, you know, you're shooting for a fifth equation that also has only x and y in it. So you really, now we are stuck with eliminating z on the second step. So I am going to take my second equation and in order to eliminate z, this one's going to be a little tougher than the last one. I'm going to have to multiply the top one by 4 and the bottom one I'm going to do by -3. So then I will have 2 equivalent equations for the top one. Right, so that's equation 1 and equation 2. So I'm going to rewrite the new versions of them. So I'll have the transformed first equation, 6x minus 4y plus 12z equals -2. So that's my first equation now transformed. And I just realized I'm calling this my second equation, but it really was equation 3 that I was starting from. So equation 3, the transformed version, is -6x plus 3, or rather a negative, I've got to change my signs here. A -3 times a +2 gives me +6x minus 3y minus 12z equals -30 and 12, -42. And now I can add those together to get my fifth equation. So I have 22x minus 7y, the z's cancel, -44, and that is my fifth equation. So my fourth equation is 13x plus 14y equals 43. My fifth equation is 22x minus 7y equals -44. Now that I've done that, I'm ready to go on to my next step, which is to eliminate another variable. Alright, so the next step is to eliminate one of the 2 remaining variables, say y. So I'm going to take my new system of equations in 2 variables. Right, that was equation 4. And 22x minus 7y equals -44 rather. And I'm going to eliminate y this time. So I'm going to multiply just the bottom equation by +2. So I will have a new equivalent equation for equation 5. The equation 4 stays the same. Equation 5 has a new hairstyle. And I can now add those together to eliminate y. So I will have 57x, the y's cancel, and 88 minus 43, negative 45. And something must have gone horribly wrong somewhere. So let me stop the tape and see what it was, because that's not coming out the way I expected. Okay, I think I found it. So I had to go back and check my work. And everything on this side looks good. But then when I did the step here, let me get a different color. Right here, this step, I distributed to here and got my 16x. I distributed to here and got my negative 4y. I distributed to here to get my positive 12z, but did I distribute here somehow? I did not. So that should have been a negative 8. So let me just back up. So this is supposed to be a negative 8. Which would mean now I would have negative 50 here. And change that down here. And I believe, I haven't checked everything, so hopefully that was the only typo. So let me go to the next step and see if that fixes the outcome I was getting. Alright, so if this was supposed to be negative 50, and then I multiplied that by 2 right here, then this is going to be negative 100, which would give me negative 57, right? Yeah, negative. So negative 100 plus 43 would be negative 57. So then I get to divide and I end up with x equals negative 1. Now that's says eliminate y by adding transformation of equations 4 and 5 to arrive at equation 6. So technically, when I did this step and I got the 57x equals negative 57, that was actually my equation 6. So I'll write that here. Then the next step says, now we have the value of the first coordinate of the triplet, which is the solution to our system of equations, because we're going to solve equation 6 for x, and then we will have the first coordinate of the triplet. So 57x equals negative 57, my equation 6. Divide both sides by 57. And arrive at my first solution value, which is negative 1. So I'm going to take that and fill it in right here. So now I got to go find my y and my z. Next step says, step 5, solve for y. Back substitute the value of x, so we know we found x equals negative 1. We're going to back substitute that into equation 4 or equation 5. Either one is fine. We don't want to go all the way back to equation 1, 2, or 3 though, because there were 3 variables there, so we would not be able to solve for y. But if I go back to one of my other two equations, equation 4 or equation 5 from this step, this and this, they have only two variables, so when I plug in a number for x, it's easy for me to find the value of y. And which one should I do? I guess I'll do the first one. I'll use equation 4. So equation 4, which is 13x plus 14y equals 43. And I'm going to replace the x value with -1. Okay, so my -1 is going to go right here. And then I'll simplify that and solve for y. So that's -13 plus 14y equals 43. So my next step will be to add 13 to both sides. So I'll end up with 14y equals 43 plus 13, which is 56. So 14y equals 56. And then I will divide by 14. And how many times does 56 go into, or how many times does 14 go into 56? 3, 4 times. No, that can't be right. Is that right? Maybe it is. Yes, it is. Okay, good. So then 4 times. So y equals 4. So now let me go back to my ordered triplet and put in 4. Okay, next I need to find z. So step 6 says back substitute the values for x and y into equation 1, 2, or 3 and solve for z. So I'm going all the way back to the beginning now, and I'm just going to use equation 1 for convenience. No particular reason. I'm going to use 4x minus y. It's the original first equation. Plus 3z equals -2. And that was equation 1. And then I'm going to replace the x value with -1 and the y value with positive, whoopsie, that's not what I meant. I wanted to do that right here. The y value with +4 and simplify and solve for z. So I end up with -4 minus 4 plus 3z equals -2, which gives me -8 plus 3z equals -2. Add 8 to both sides, and that gives me 6. Then I'm going to divide by 3 there, right here. So I get z equals +2. So let me go back up to my ordered triplet and complete the solution point. Now, I'm not done yet though, because I still need to check my work. I need to check my answer to make sure that it works. So with my first equation, which was 4 times x minus y plus 3z equals -2. I need to verify that by plugging in the -1, the 4, and the 2, and making sure that I get a true statement when I simplify. So this will be -4, -4, +6, so that's -8 plus 6, which is -2. All right, so that checks out. And this has to happen all 3 times. So the next equation is 3x plus 5y minus c equals 15. All right, so plugging in again, -1, 4, 2. This will give me -3. This will give me 20, +20. This gives me -2. So then I get +17 minus 2, which is 15. So that checks out too. One more. Just got to get all 3 to work out and make sure. So that's -2x plus y plus 4z equals 14. Coming in with my coordinates. I get 2, 4, 8, 6, 8 equals 14. Yay! So cool. All done. Okay, so quick recap. Solving a system of 3 equations and 3 variables. I won't say it's easy. It's long and tedious, and you have to be very careful not to make any mistakes. And if you do find something isn't working out, you've got to be able to go back and retrace your steps. So your work has to be very meticulous. In my solution, I made an error in one of my steps, and I had to go back and find it, which I did, and that was no big deal. But if I did not have good organized work, it could have been a real nightmare trying to figure out what went wrong. And most likely I would have had to start over completely. So what you want to do is keep really nice, neat, organized work, and that's what this handout is meant to help you do. So the main steps, we're starting out by visualizing what the answer should look like in the end, and then going through the process of eliminating one variable, then eliminating another variable, then solving for the remaining variable. So you go through getting rid of one, getting rid of a second one, and solving for the leftover one. And I could have started with eliminating x first, I could have eliminated x first and then y second, or x first and then z second, any combination. It really depends. When you look at your system of equations, you can make a judgment call what you think is going to be the best way to go. But even if you stick to this particular template of always getting rid of z first and then y and then x, at least as a beginner, if you want to stick to that, it will work. It just may not be the most efficient way. Some solutions or some systems, it'll matter which variable you get rid of first and second. You could have a really easy time of it if you make the right judgment call, or you could have a really lengthy, frustrating experience if you make the wrong judgment call. But I mean, honestly, in the end, as long as your work is clean and correct and well organized, you will get to the correct answer no matter which variable you choose first. And I did it like, let's get rid of z, then y, then we'll have x, and then once we have x, we'll go and use it to find y, and then use it to find z, and we end up all the way back at the beginning. So I think that's a really good way for a beginner to learn the process. So what we did is we visualized the final answer. We eliminated one of the three variables by using two equations at a time. We transform them by multiplying them by something if we need to, and then add to get rid of z. We do that twice, giving us two new equations. So we end up making ourselves a brand new system of equations, a system of two equations in two variables. And then we eliminate a variable again, which narrows us down to just the one variable which we can solve for. Now once we have one value, it's like we've just found the key to go back and unlock one of these and find out what y is. And then once we know what y is, we have x and y in order to go back and figure out z. All right, so I hope that helped, and let me know what you think of this helpful tool that I designed. I'm proud of it. I spent a lot of time on it, and I'd love to hear students say, oh my gosh, Professor Stevens, thank you so much for making that, because now I feel like I understand what to do. Yeah, that kind of feedback's awesome. All right, guys, thank you. Oh, and also, while I'm at it, if it's not working for some reason, that's extremely helpful as well. So please do share constructive criticism, whether it's, singing my praises or suggesting some changes. See you in class.